Absolutely.
This afternoon. I hope you all had a good lunch and aren't feeling too sleepy post large meal that we had. Well, without further ado, we'll get started with our session today. Title of the session is Enhancing Weather and Climate Monitoring Capacity Through Collaborations. We have a number of presentations today, 5 different presenters, all related to monitoring technologies and collaboration within the atmospheric domain. I have the pleasure of starting us off. My name is Kristine Confalone. I am the manager of the Collaborative Monitoring and Partnerships program within the Meteorological Service of Canada. So I'll just pull up my presentation here. And if folks online, if you're having any issues or can't hear us, please let us know. You can write in the chat if you can't hear me. Hopefully you can. So as many of you likely know, the Meteorological Service of Canada operates a number of surface weather monitoring stations across the country, collecting a variety of different parameters, largely standardized. The network is comprised of about 585 stations that are distributed across the country based on needs to meet our forecasting and climate research purposes. But as we know, Canada is a very large country with a very vast and diverse environment, and we recognize that it's quite challenging for one organization to monitor it in its entirety. And this is where the Collaborative Monitoring Initiative was born. So about 10 years ago, we started this program that is really designed to facilitate access to weather and climate observations from a variety of different network operators. So we're looking at working with organizations outside of ECCC who also collect weather and climate data, bringing that data into our systems, making it available for use internally and externally. And our vision with this is really to strengthen our national capacity to monitor through collaboration and increase in collaboration that we've had historically with our provincial and territorial counterparts, as well as other federal departments and any other network operators across the country. We do this through the mechanism that we use is a memorandum of understanding, which helps us solidify some of those relationships. And about 5 years ago, we established a national coordination forum that brings together representatives from provinces and territories and the federal government to talk about standards, best practices, how we can collaborate and make the most of the data that we're collecting. So under the Collaborative Monitoring Initiative, there are a number of partnership models that are possible. The main is data exchange. So this is really where we're looking at sharing data, making the most of the data that's there, looking at how we can make it more accessible, improve the quality, make it more interoperable. And this is really the baseline of our program. The one step up from that is something we call integrated network planning. So this is where, as network operators, we're looking at how we can optimize the existing investments we've made and really look at where we can potentially reduce redundancies or address gaps in our networks. And one step above that is joint network operations. So we're actually looking at potentially how we can work together and share the costs for new or existing stations based on our needs. So there are a number of benefits when it comes to this program on the client side. Of course, I've talked about increasing access to data to help support our programs, our forecasts, as well as our partner or clients' products and services as well. Also looking at how we can improve data quality, right? Looking at how we can promote national standards, best practices, and really work together to share information and various research and development we might be doing. On the operational side, the idea of potentially having some more effective monitoring and networks. So this is where we think about those gaps and redundancies I talked about, as well as how we can look at installing new stations in maybe remote or more difficult locations for one organization to monitor on their own. So in terms of status for the program, we have signed a number of agreements with provinces and territories across the country. So we have data sharing agreements with BC, NWT, and Saskatchewan, and network planning agreements with Yukon, Newfoundland, Labrador, New Brunswick, Nova Scotia, and Ontario. Although we do have some historical agreements with Alberta and Quebec that are in place that help us work with those provinces. And we're working on finalizing our agreements with Manitoba and PEI hopefully this year. When it comes to data sharing, this is largely guided by open data policies and a principle of no quality. So typically we share data using open data policies across the public sector that are in place across most provinces and territories in the federal government. We bring this data into our data management system, or DMS. We quality assess it in real time and make it available. You can see sort of a very simplified data flow diagram on the right-hand side there that just shows how we bring the data into our systems and then push it out to both external and internal users. It's important to note that through this program, we're really sharing data under this principle of known quality. So there's no minimum quality standard, but what we're trying to do is work together to make sure that the appropriate metadata is available so that users can make informed decisions about what data they want to use for their purposes. When it comes to actual data that has been brought in and made available, so currently we're looking at about just over 1,700 stations that we've been able to bring in to our systems and also push out externally. So the map is slightly outdated here, but shows you a little bit of distribution through different networks across the country. And we're also pushing that data available externally, as I mentioned, mainly through the MSC Data Mart and GeoMap platforms. So there's a number of provincial and territorial data sets that are there right now for people to use and for their own applications. The next big piece, so as I mentioned, we initiated this governance body that we call the Canadian Council for Weather and Climate Monitoring, or CWAC for short. It was established about 5 years ago, and this is where we have representatives from each province and territory, as well as each will see that meet on a regular basis to talk about our monitoring networks, any challenges that we're facing, share innovations or transformation plans, and really talk about how we can improve collaboration. To date, that's really focused on the data management side of things, so how we collect the data, but also how we quality assess the data, how we store and share our metadata, and how we disseminate that data to the public and to clients. And there's 4 main pieces here that I'm going to talk about in a little bit more detail with respect to priorities or activities that are happening underneath the Canadian Council for Weather and Climate Monitoring. So the first one is this report on snow monitoring in Canada. So this, the intent here is to develop a national report that provides an overview of current snow monitoring networks, provides a summary of needs and requirements around snow data, and identifies some recommended areas where improvements can be made. And this was really born out of a conversation at one of our CWAC meetings around the challenges in not only collecting snow data, but using it and the variability in the ways that we collect snow data across the country, depending on where you are, what equipment you're using, and what you're using that data for. If folks are interested, I will say a little to learn more about this report. There is a presentation tomorrow afternoon in one of the snow sessions that will be going into detail on exactly what's in this report and some of the preliminary findings. For now, just as a quick overview, we have a group of representatives across the country that have built this report, mainly built off of results that they got from a survey that was disseminated to network operators. And they provide a summary of those networks, the equipment, challenges, and recommendations. And we're anticipating this report to be published this fall, 2025, and it will be publicly available. The next piece that I want to talk about is a national dataset catalog. So this initiative is really focused around improving the data discoverability and accessibility piece that I mentioned as a key priority for CWAC. So we're looking at how we can develop a national publicly available resource that can point users to different data sets they might be interested in. So we actually launched this in fall of 2024. There are currently 32 data sets that are on the dataset catalog right now, and we're continuing to add and complete this over time. It's available through the ECCC data catalog, and it's sort of a subset in there where you can find information about different surface weather and climate monitoring networks across Canada. In terms of next steps, we're looking at publishing an additional 40 data sets in the upcoming year. And as I mentioned, we'll continue to update it to make sure that the most recent and up-to-date information is available. The next activity I'll talk about is a national metadata strategy. So as I mentioned, a key piece under this program is this principle of known quality. And we're looking at how we can improve the metadata that's available. Not only is data sometimes inaccessible, but metadata is also very difficult for people to find and access to make those decisions about what kind of data they want to use. So what we've done here is we've developed a high-level strategy that guides how we're going to collect and disseminate data from those participating monitoring network operators through CWAC. And we've developed an implementation plan that will be phased through a tiered implementation, mainly to recognize some resource constraints within our partners and making that metadata available. We'll be using the WMO's Oscar Surface tool. So this is an internationally recognized tool that follows a international metadata standard that also aligns with the Canadian metadata standard to make this information available so that detailed station metadata like instrumentation, any kind of sighting characteristics around the station that might impact observations can be made available through this strategy and through this tool. So in terms of next steps, we are moving into the implementation phase right now and looking to make tier 1 metadata, which is essentially kind of baseline metadata, available in Oscar Surface by the end of this fiscal year. And the last activity I'll talk about is a new one. It's a national archiving strategy. So again, really focusing on some of these data management pieces. There's a recognition as well that right now it's very difficult to access historical weather and climate data from different networks or different data sets across the country. And we're looking at how we can develop a coordinated approach to a national archive. What that looks like yet, I do not know. That is to be determined. But we're hoping that that can help improve, again, the accessibility and availability of historical data that's available for climate analyses. So right now we're developing a project proposal that will be reviewed and approved over the summer. And then we're hoping to initiate some of this work starting in the fall. We'll set up a similar to the snow work group. We'll have a working group that will work on developing this strategy, and we're anticipating that it will probably take about 2 years to put this in place and develop a path forward. Okay, so in summary, there's a lot of pieces here that we're working on to look at how we can address some of our gaps, not only in network monitoring operations, but in data management as well. So the pieces I talked about around national metadata strategy, putting that into practice, publishing this report on snow monitoring, and developing that national archiving strategy to look at where we can go in the future to make sure that more data is available for climate purposes. And finally, we're continuing to look at data services as well for how we make this data available, how we disseminate it to the public, and how we can streamline some of these processes to make more and more data available as we continue in the future. And that's all I had. So we'll move now to a bit of a question period. If anybody had any questions for me on this particular topic. No questions? Anyone online? No. Okay. All right, thank you. Okay, so next up I will introduce our next presenter, who is Jean-Thomas Deneau from Agriculture and Agri-Foods Canada.
All right. Thank you very much. Good afternoon, everyone. It's a pleasure to be here, and thanks for Kristine to giving me the opportunity of presenting the work we've been doing recently. At first, I was planning of doing a poster and presentation. That's the thing is we don't have a lot of results to show, but I think the process of the project might be interesting for this session. So, Jean-Thomas Deneau, I work at Agriculture Agri-Food Canada based in Quebec City. This project is done in collaboration with many people, and we have Trevor Coates and Matthew Richards in Lethbridge, who are my main collaborators for this section. But we also put on board 3 people from Shared Services Canada to work on the technical aspect of the cloud solution that we've been working on. So the project is about the best practices for Internet of Things agricultural sensor networks to support on-farm decision-making. So basically what I will be doing is just go back to the purpose of the project, explain exactly the rationale, what led to us presenting that project. We'll do a small insert on the Internet protocols that Internet of Things protocols that we've been using, which is called LoRaWAN. And then shortly go into the data flow and architecture and the first lessons we've learned in that first year. So basically, as many organization, AFC has research priority put out in the strategic plan, and one of those priorities is about accelerating digital transformation. What does it mean? It means that we are looking at creating or supporting information-based or information support decision for the agriculture or agri-food system, or the whole chain of production. That means also it can be working with genomics. It can be working with imagery in terms of detection of pests and diseases. But in the agromet field, we propose a challenge of working on improved tools to collect, interpret, disseminate on-farm data to producers and researchers. The idea is that we've been in the last decades very good in working with heavy-duty equipment, so data logger-based reference data station with high-grade sensors, and we've been very good at putting out information that is high quality, ensured quality control for our purposes, either projects or tools. But we've been having difficulties in terms of disseminating these kind of information. On the other side, the industry has been very good at creating new tools and devices that are maybe cheaper in terms of grading of quality of sensors, but has the abilities to be visualized online rapidly, and creating all sorts of information for producers and the industry. So the idea of the project is really to link and try to link the benefits of both network stations, so the high quality stations that we maintain, and with specialized network of sensors that can be supported or extending the information coming from our traditional research network stations. So the scope of the project is to build a proof of concept showing the integration of reference sites. I use tier 1, it's probably tiers 2 or 3 or whatever, based on what you just showed, and a distributed Internet of Things sensor nodes to assess soil moisture and supporting agricultural quality parameters. We selected soil moisture since it's a very complex parameters to follow. It's highly spatially variable, so for us it was a good parameter to follow. Since it's a proof of concept, we located our research on AFC's research facilities, and we have been using the RISMA sites, which is the real-time in situ soil monitoring for agriculture stations. And the goal is to develop data standards and best practices for data collection using Government of Canada cloud environment tools in collaboration with Shared Services Canada. And the name of the team is the Digital Enablement, well, that's a hard one for me, Science Program Cloud Team. 3-year project, we just completed 1 year. For those who don't know, this is a map showing all the different facilities that AFC is currently operating. We have 20 research stations across the country, plus 14 different research farms. And on top of that, we have the RISMA sites, which is about 35 real-time soil moisture stations, mostly located in the prairies. But we have also 2 sites in Ontario. We chose 3 sites out of those, 2 that has RISMA stations and 1 in Lethbridge, based on the location of the lead scientists, and also that has soil moisture, long-term soil moisture monitoring at that station. Here is a map of the different Internet of Things protocols that is available, and most of them, I guess, are common for all of us. It's showing on that graph the different characteristics based on the range of the information that is transmitted, the amount of information at which you can transfer information. So that's the data rate, and the power consumption. And you see that cluster of protocols that is available that that aims at transferring data on the long range using very low power, where LoRaWAN is standing. LoRaWAN stands for Long Range Wide Area Network, is a modulation of the radio frequency at 915 megahertz. So it's an unlicensed band in North America, and on which you have all the media access control protocols to allow for machine-to-machine communication. So the LoRa network architecture is usually based on 4 components, and so separated in 4 components. We have on the left side, we have the device or the nodes that are attached with the probes on which you'll be measuring the information that you want. This information is pushed or received to a gateway, and that's the device that is connected to the internet. And for these 2 to be communicating, they have to be identified on the network server. So that's where the decryption occurs. So and the handshake communication occurs between the device and the gateways. That's also the step where you can translate the information, which is only small bytes of data, into human readable information. And from that step, you can push the information to the front end side of the service, so the application server, and where you can build your own whatever graphs, visualization, and tools that you want to do. Data can be coming upward, so using uplinks, but you can always send comments to the devices on the ground, or even trigger action if needed. This is just an example of the devices that we've been playing with. On the left-hand side is a gateway. So basically, that's the device, like I mentioned, which is connected to the internet. Once it's configured to the proper network server, you can forward information to the cloud. And on the bottom, you see the different examples of grants or just nodes that can be hooked to any kind of sensor, mostly used in agriculture or even meteorological monitoring. So you can use pulse counts, analog reading, digital readings, such as the SDI12 information. So you can hook up not pretty much anything, but close to. What's interesting is the price tagged to those devices. Gateway is probably the most expensive element in the field, ranging between 700 and 2,000, while a single node range between 75 and 200, which is pretty cheap. In the agricultural setting, we have easy access to high points in the environment, and that's just an example of where we've put some gateways in another project. That's giving us the opportunity to really explore the full range of that technology. While on the ground, we can have different kind of setups for sure, but this is really the simplest that we've put out, just a rain gauge and soil moisture probes on the edge of fields that can be spread across the landscape. In terms of data flow, this is just the high-level map of how things are happening. So we are using the cloud space offered by, not offered, but maintained by the Shared Services Canada, which is now kind of centralizing our cloud environments in the federal departments. We have installed different instances on that cloud environment. And this is maybe a message I can pass to other federal employees in the room, is that this is an environment that is made to be deployed easily or extended to any kind of other user that might be interested in using this kind of technology. So in terms of instances, we have the network servers part, which is using the ChipStark network server algorithm or software part, which is an open source part as well. But we're also hooking it up to the MQTT broker that has all the security aspect to make sure that the connection is highly secured and respecting the standards of the government of Canada. That's where the message gets decoded, and then it's pushed in two environments. So we have a S3 bucket that receive all the payloads for archive purposes, but the relevant information is pushed into a structured database. It's called Influx. It's another open source tool in which you can pull the timestamp information to further analysis afterward. Final piece is the visualization tool, which is done using Grafana, another open source tool that allows us to prepare either dashboards, graphs, analytics, any kind of information that might be relevant for the stakeholders which will be providing the information. So that's the part that we still have to build. We're up to that stage at this time. So I don't have any fancy graph to show you, but you understand the flow of the data. So basically, like I mentioned, we have a current architecture that is designed to be replicated and extended depending on the needs. In terms of the LoRaWAN protocol, we're quite happy with the premises. So it's mentioned that it can be up to 15 kilometers, but we've been reaching over 7 kilometers reach without any lot of data loss. And it's been using very low power as well. So all the batteries of the devices have been surviving the winter. It's been promising on this end. And of course, the evaluation of the value-added information real-time analysis to support on-farm is still to come, but we'll be happy to be preparing a little talk for the next year. And that's it.
Very much. Does anyone have any questions to ask?
varies so dramatically even down to the field scale. I'm wondering, have you done any experiments to see how many sensors you need to represent the conditions for a given farmer?
That's a good question. I think, and we expect that it's going to be highly variable. And that's the thing, is that we still need to figure out what would be the best information to derive from the soil moisture. And like, do we use the raw or the actual value coming out of the sensor, or we do kind of either average it between sites? Do we derive what would be the highest point to the lowest point to maybe inform on the water availability for crops and stuff like that? So that's the information that we want to make sure that we provide to the stakeholders to inform decision. Right? So the raw information is not that kind of useful for most of the people. It's really the derived information that needs to be tweaked, if it makes sense. Gateway.
And if I got maybe a telemetry system for that base station to kind of communicate via satellite, would that potentially be functional in those sorts of environments?
Yeah, the gateway can be hooked to I'm not quite sure, but probably can be hooked to a satellite and whatever, as long as you get that base station hooked up, and then this device it's made to receive information from thousands of sensors. Again, it depends on the environments. Like, we are in open fields. I'm pretty sure, like, well, in urban environment, they mentioned that the scale, well, not the scale, the range of them is limited. I'm pretty sure that if you go in densely or forested area, probably will be limiting the range of the transmission. But yeah, it's made. I mean, the thing is with LoRaWAN, it has to be silent 99% of the time. So it's very small bytes of information that can become. So that's why you can look up a lot of sensors.
Very much. So I'd like to welcome up our next presenter, Lynn Engel from the University of British Columbia. Thank you.
This has a laser pointer. There we go. Very faint. Okay, hello and welcome to my presentation titled From Deep Freeze to Chinook Breeze, Enhancing Winter Weather Forecasts in the Peace Region. I'd like to start by thanking my main funding sponsors of my tax and BC Hydro. I will start by giving a brief overview of the project. Most of the presentation will be focused on the recent fieldwork of last winter. On the index map, on the corner, you can see the outlines of the provinces of British Columbia and Alberta. The Peace region is situated in the northern part of these provinces. On the main map, for scale, you can see the city of Edmonton, Port Nelson, and the Rocky Mountains. The Peace River's watershed starts in the Wilson Basin, continues east by Fort St. John. Fort St. John is also the location of the new Site C hydroelectric dam. The river continues and turns north at the town of Peace River. Now, every winter season, the river freezes from the north, continues south, and can even reach the Alberta-BC border. For this field trip, we flew into Grand Prairie and drove to the town of Peace River. BC Hydro has two main concerns. The first is the ice jams and related flooding hazards to the local communities. The second is the optimization of hydroelectric power. As this region is remote, you may not realize that this is a significant asset to BC Hydro. It represents a significant part of power generation to British Columbia, and most of this power is transmitted to the population centers on the West Coast. BC Hydro desires improvements in the temperature forecast to the 3 to 4 day range. This is because it takes this amount of time for water to be released at the dams upstream to affect the communities of Alberta. There are several challenges with current day temperature forecasting, and some of these are very cold Arctic air, warm downslope winds, and changing for topography at different scales. For instance, you have the river valley itself, which can change 250 meters, and then the extreme scale, the Rocky Mountains. And the Rocky Mountains are the cause of the downslope winds and help dam the Arctic air. Currently, modern weather simulations are being developed to improve the accuracy of extreme winter temperature forecasts. One of these tools that we're using is the Weather Research and Forecasting Model. Another challenge, which is the theme of this seminar, is the lack of direct observations, especially in the river valley. There are 3 airport weather stations in this region, but they exist on the adjacent plateaus. And I can tell you from being there that there's a microclimate in the base of the river valley. Now, in the river valley itself, there's no major weather stations, but BC Hydro and the Water Service of Canada operate 5 digital collection platforms. You can see them as the diamonds, but they only collect temperature data. So there is no, and I mean 0, wind or humidity data within the Peace River Valley. So we designed some field work to go and collect our own data, and this is going to be used to validate our forecast models and for future AI and machine learning, our training models. This is a graph showing ice front location versus time, and there's 2 things to notice on this. One is the scale is in hundreds of kilometers, and the second is all these light, faint historical lines to show you how variable this ice front location is. The 2 circles represent the 2 field trip dates that we went out there. Now, air temperature is the primary variable influencing ice forecasting models. And the first field trip happened under a warm air mass, and so the ice front actually melted and backtracked. The second field trip occurred during an Arctic air mass, and you can see how rapidly the ice front moved. Okay, so this is the equipment that was used. We had a helium-filled balloon, a radiosonde, which is a styrofoam coffee cup. You need a field computer that can handle the elements. There's a radio antenna, so you are live. You can see the data coming on. So if the data is like poor quality, you can launch a second balloon, or a third, or a fourth. This windsonde equipment was designed by Sparv, and that's a company in Sweden. And I just wanted to emphasize how portable the system is. This is a laptop for scale, and so that and the batteries had to go into carry-on, and the rest of the equipment could fit in a luggage container. You also need to have a truck and a tank of compressed helium gas. Winter driving skills are a must in this environment this time of year. You need a headlamp because the daylight is very short in January at this latitude, so many soundings are done at night. You need cold weather gear and lots of hearty food. So let's travel to the Peace River and watch a launch. See the balloon coming up? There's a little cup underneath it. It's hard to see on the screen. We designed this to have a rise rate of 2 meters per second. This is quite slow compared to the international airports. And that's because we wanted to have a lot of data points and high resolution at the most part of the atmosphere. And we did this to measure different surface and weather conditions. And I'd just like to take a moment to thank my field assistants and fellow grad students of Mina Deschler and Melissa Westland. And we were very lucky to record data in the deep freeze and the Chinook breeze. So during our Chinook breeze, our warmest surface temperature was +7, and our coldest was -32, which is a difference of 45 degrees Celsius, which when you stop and think about it is pretty wild. So underneath are two QT diagrams of the sounds. The temperature data goes on the slant for the skew. The light blue represents the 0 degrees Celsius. The red line is temperature with height, and the green is dew point. So for this particular graph, these two curves are far apart because the Chinook has quite dry air. This other diagram is during the cold, so we had -32. You can see that the very extreme cold was a shallow layer near the surface and had a very strong temperature inversion at the top. I also wanted to say that these particular days were like the happiest moments of the field trip because the warm breeze would almost blew me over, and the colors at sunset was amazing. And on this particular one, it was just so satisfying to be able to collect data on this very challenging environment. We also measured data when the water was open water and when it was frozen. We also had other interesting weather events when we were there. We had an air mass change from warm to Arctic air. During that transition, we had a snow grapple convective storm hit us. This is the sounding from that. And in this particular case, the curves are very close together. So high relative humidity and in the snow growth region, which is how you get your precipitation, and the grapples, because it just partially melted some snowflake, it hit over the 0 line and then refroze. We also saw turbulence. We had a rapid warming event of 20 degrees Celsius in less than 12 hours. We had ice fog, which is quite unusual. This is the best picture I could get because it lifted when the sun came up. But this is a fog. You're in a cloud and it's -24. Everything frosted up. That was quite interesting to work in. And again, the temperature inversion at the base. So to summarize the field work, we were there for 15 days. We collected 34 soundings in 5 different locations. Now, these are hard to see. There's the red stars on the map, 1, 2, 3, 4, 5. Our base was the town of Peace River, where most of the soundings were located. On this map, we also have the ice front location. So January 27th, it was here, and February 9th, it traveled there. The heights, the heights we reached, again, we used a slow, high resolution in the shallowest part. The highest height we reached was 370 hectopascals, and our average was 540 hectopascals, which is about 5 kilometers above where we launched. So working in cold weather is difficult. For every degree colder than -15, everything gets harder and takes longer. These photos here on the left are on our last day of our first field trip. The Arctic air mass came, so it was about -15, and we got no GPS, probably due to the power drain on the batteries. So we had a week between field trips to get advice and to brainstorm. And so what we ended up doing was using cotton balls and stuffing them inside the sound to try and keep it as warm as possible. On our first day of our second trip, we popped 6 balloons in one morning because it was so cold that the latex balloons were very fragile. So we improvised by using cotton twine to gently tie them. So this turned into a 2-person 4-hand job. And when it was really cold, we improvised by halfway through the sounding, we ran up to our room and put the antenna outside a window on a metal baking tray from our kitchen. And so us and the computer could stay warm. So to conclude, it is challenging to collect data in the winter. So please contact me to collaborate. This sounding information is available. So if you or anyone you know work in these environments, this data might be helpful to you. Also, please contact me for a future collaboration. It would be wonderful for me to expand this winter program next winter with additional. And final thought, the Peace region is vital to Western Canada and warrants increased research and resources to ensure a resilient future. Thank you. Yeah, no, it was different because you can't see the temperature when you're at the surface. So seeing how cold the layers were or how warm, like sometimes it was like 12 degrees above us, like 600 meters up, which you wouldn't have guessed. So, and I'm still looking for the data. This is preliminary, but I saw some turbulent clouds. I'm looking forward to digging through to see the clear air turbulence. So.
Yeah, just yes, okay. How about the use of remote sensing? Is that not an option to collect some of the assets that
Yeah, it would be great. The thing with remote sensing, you don't always know what level you're at, like what depth, because the temperature can change depending on what vertical level you're at. But also need to verify that the remote sensing is working, and still the lack of ground surface observations make that a little difficult, but I'm open to all sorts of things. I've been taking lots of talks here, learning what other information is available. So I hope so.
Any other questions? Right on time, I'd like to welcome our next presenter, Quinn Sapin from Queen's University.
All right. So hi, I'm Quinn. I am a second-year master's student at Queen's University under the supervision of Professor Elise Devois. And for the past year and a half, I've been working on improving the measurements of unfrozen water content in cryonic soil, so that is permafrost, or at least permafrost decaying permafrost, through the use of quantitative modeling. So this presentation is going to be storytelling about what happens when you find some issues in the literature and how to use quantitative modeling to tackle them. So unfrozen water content in cryonic soil is described with a physical relationship that's called the soil freezing characteristic curve, or for short, an SFCC. This curve will merely come to relate the unfrozen volumetric water content, theta in Y, to the soil temperature, T, in X. So the idealistic SFCC would look something like this, where there's very distinct freezing and thawing in. This makes this characteristic hysteretic behavior. Measurements like these are of great interest for individuals like engineers when they want to make informed decisions about the type of foundation that they'll put in permafrost decaying region, or for individuals that are interested in the regional water focus activity, since the flow of water through ice-rich is quite different through the flow of water through ice-rich layers is quite different than going through ice-poor ones. So before delving into the actual characterization of unfrozen water content, we need to talk about the converse phenomenon of unfrozen water, which is, well, frozen water, so ice. So if we come to represent our system of saturated soil, we have this simple kind of diagram with three phases, where we have a water phase, an air phase, and a soil phase. Upon giving it the proper conditions to create ice, where do you think the first ice crystal would appear? Would it be within the free water, at the interface between the air and the free water, at the interface between the soil and free water? Well, that's actually a little hard to predict because there are many factors in play that can both inhibit and facilitate crystal nucleation and equilibrium on all these different sites. And that's because the thermodynamic of crystal nucleation is not quite about whether something happens or not. It's a lot more about the likeliness of it to happen and the likeliness of it to occur. Even if we don't quite bother ourselves with the exact size of nucleation within our system, it's actually a little hard to assess the state of water in minus temperature changes. So in this little activity I'd like to have with you, if we put an arbitrary amount of soil in a glass of water at room temperature, you'd feel quite confident telling me that it's completely unfrozen. If I lower the temperature down to 4 degrees, you'll still be confident telling me it's completely unfrozen. As we reach 0 degrees, you might start to speculate that there'll be a little bit of ice. And as we lower further down the temperature, -2, you'd say there's substantially more ice, but that would be difficult to predict exactly how much. And then at -10, you'd feel confident telling me that everything is frozen, or at least only the residual unfreezable water remains. So in essence, there are set points of temperature that we can be quite sure of the state of water, but anything in between is our best guess. The reason for that is that assessing the phase change of a crystalline structure, like ice, is quite a complex thermodynamic phenomenon to predict, especially in the freezing limit. The reason for that is that the condition to obtain this first trigger of an ice crystal to nucleate, exist, and remain in equilibrium requires to surmount a certain level of activation energy, which makes water quite easy to supercool. The other phenomenon that interested the file experiment was this amount of unfreezable water that remains at very low temperatures. So there is water that is so strongly bounded to particles or surfaces that the molecules cannot be really rearranged into a crystal lattice, so it's very hard for it to freeze. But once again, exactly how much and at what temperature remains difficult to predict. These are usually the type of question you try to answer when you make a soil freezing characteristic curve. You try to see where's this first trigger of ice nucleation, what's the first temperature, and how much residual water content there is. So because of this complexity, and because observing ice in a soil system is actually quite difficult, we always use indirect measurements to assess unfrozen water content. In our case, we use a capacitance-based sensor. That is a sensor that will inquire about the physical property of the soil and then transform that into what we actually want, the unfrozen water. In our case, that is dielectric permittivity. So I'd really like to stress that because, in essence, we are never actually measuring the unfrozen water content in the soil. We're always measuring a value that is indicative of it. So we always need to convert it. So we need something called a conversion curve. To stress, again, what a conversion curve is, I have a little activity that I'd like to do with you. So if I gave you these apparatus and asked you what they all measure, you'll probably feel quite confident and tell me that they all measure temperature. But once again, that's not actually exactly true. All of these use a proxy measurement to report temperature. So for the physical thermometer, that'd be the height on the side. Then for the 221, it'd be some sort of voltage measurement. So for the physical thermometer, the conversion curve is in addition on the side. If I gave you this thermometer and asked you to report to me what the temperature of the room is, you'd feel quite confident doing so. But if I gave you this one, you might not. And the reason for that is that the conversion curves, so in addition on the side, all kind of messed up. They're unevenly spaced out and they have very visible numbers. And that is the core of what I'm trying to convey here is that if you have an apparatus that requires a conversion curve, if that conversion curve is either inadequate or not great, well, the measurement becomes unreliable. That is essentially the core of my project because the default conversion curve on soil sensors is quite inadequate, or at least in my belief, inappropriate. So whatever they use to transform dielectric permittivity into unfrozen content doesn't quite apply. So the goal that I had given myself was to find a model that would encompass soil parameters that would be characteristic of samples, which would allow the conversion curve to be transferable from one to the other. And so sometimes when you're given some sort of apparatus and you see that the wheels on it aren't that great, you do need to sometimes reinvent those wheels when you find it necessary. So the current curvature curve in the sensors is the top 1980 equation. It is a third-degree polynomial empirical fit. And the big issue with it, it's not really transferable from one system to the other. Why is that, you might ask? Well, I'll ask the question back in return. What do you think all of these different numbers mean? Are they soil parameters? Or there's some sort of characteristic about the data? Well, if you break down what a third-degree polynomial is, you have your variable, which in our case is epsilon, which is the the sample's dielectric permittivity. So they're all over there with different powers. And then you have A, B, C, and D, which are, well, the constants. And so they are your fitting parameters, and they're exactly what they are. They're meaningless numbers that have just been decided through your fitting algorithm. And so the problem with that is that you cannot possibly alter these in any significant way to use them on a different system. So not only do we have an empirical third-degree polynomial fit, but, and I'll make a dramatic pause, it is not rated for below 0 degree temperatures because it is a third-degree polynomial fit that was done on wetting and drying curve. And since we work on permafrost decaying region, we are only interested in chaotic conditions, so only for temperatures below 0. So essentially, it's an empirical fit that's been extended way beyond its domain. I'd like to argue that we can do a lot better to transform our dielectric permittivity into unfrozen water content. So if we were to use something like an adapted mixed model, we could come to represent our system with this fancy weighted average that represent uniformly rounded particles that are randomly oriented in the background phase. In order to do that, we need to represent our system as follows. So essentially, saturated soil in chaotic conditions can be represented as follow, which is essentially a free background, a free water as the background, in which we have a few soil particles that have strongly bounded water and some ice and some air particles. And so hopefully, as we use that with the Civilomics model, we can give some sort of statistically representative value for this entire thing. So here's the most important slide in my whole presentation. So this is the actual solver. So this is the part that does the transformation from dielectric permittivity to unfrozen water content. So we have our system equation on the side. And if we were to input some metadata from our samples, we could come to represent the strongly bounded water content. We could then use that into our adaptive dielectric equation for the water phase. Now, we need to use our best guess of what we think the water phase has as a dielectric permittivity for this specific data point and solve our Civilomics model with it, which we would then obtain a volumetric unfrozen water content. We can use the volumetric unfrozen water content, the other equation, the adaptive dielectric for the unfrozen water, and see what the actual dielectric of the unfrozen water is, and then we keep on going. As we run this loop, eventually we should be able to see that from one iteration to the other, we should agree. And that's where we know that we've correctly solved our system with the correct volumetric unfrozen water content. And so that's for one data point. So as you move to the next one, you start over again and you get to use just the previous iteration of unfrozen water content dielectric permittivity. Prior to even being able to use our solver, there's actually a lot of pre-processing that has to be done. So if you start with a raw dielectric, you need to assess the temperature, the systematic error in your sensor in terms of temperature, apply that to your data. Then you need to find the equilibrium point, that is where the temperature stabilizes, call out the equilibrium point, and then finally get to use your solver to finally get what you want, which is SFCC. So it's all fancy, but what does this all do? Here are some results from a freestyle experiment that I've run in the lab on some silica flower samples. And it is no surprise because when you convert numbers to different operators, well, usually they are different, but exactly how much different? Oh, exactly this much. So essentially, the default curve, so the top 1980 equation, dramatically underrepresent the amount of residual unfrozen water content by about 10 unit percent. When I say unit percent, that's because, well, top will say there is 5% residual unfrozen water content, but the converter that we've developed says there's about 50. And yes, that means this is about triple the amount of unfrozen water. So we've come to apply this conversion curve in this process through a lot of different samples. So here, for example, I just added a high organic soil content, and essentially they map all over the place in the domain, but this 10% discrepancy always remains. Actually, it's a lot more data. It becomes a little legible when there is so much of it, but this 10% discrepancy with top is always present. So the conclusion of the current state of my research is that we can definitely use an empirically grounded quantitative model with representative parameters from the sample metadata, coupled to an adaptive dielectric mixing model for the unfrozen water phase, in order to process raw dielectric permittivity value to volumetric unfrozen water content values to get FFTCs. The current results showcase that top 1980, the default conversion curve, dramatically underrepresent the amount of unfrozen water content at low temperatures, about 10 unit percent. This means there's nearly triples the amount of unfrozen water content. And as just a closing statement, also as we were building the quantitative model, adding some correction for such as the adaptive dielectric mix for the unfrozen water and some volumetric correction definitely has altered the curvature of the SFCC in the domain more closely towards the 0-degree axis. So.
Gwen, is there any questions? Yes, go ahead.
Is it possible to use this without necessarily following all of the steps? Is there performance that sometimes have a solver that you can kind of plug in instead of that third degree column that you use easily in
Yeah, absolutely. So, okay, great. So that's the static representation of what the solver does. Everything is currently in MATLAB, which I kind of patented throughout my degree. It works because I'm here and presenting something, but it's not the most user-friendly thing I've ever done in my entire life. But I'm working on making it better, and I would definitely hope that individuals could come either, and the fun part about the top equation is that it's a non-equation, so even if you don't have your raw data, you can still take your volumetric reservoir content and back process them into the raw data, and then use it to kind of properly convert them. So yes, the goal would absolutely be to kind of provide researchers to convert their current, even their old data, using this model instead of the top 1980 equation.
Was that a great question?
Right. Yeah. Yeah. No. So unfortunately, so the part, for example, let's say all the teros and different like meter sensors, is that they automatically make that conversion for you. So because what they really read is logic permittivity. Actually, that's not even true. It's actually amount of seconds into logic permittivity, and so they automatically made that transformation for you. So no, this would have to be done out of the field. I mean, unless you're running with your laptop, and but that would be, I understand, appropriate.
And one final question.
You mentioned that what was the temperature range in both content?
What do you mean by temperature range?
Like, so you were saying that like the other model for one volumetric water content was completely outside of its range.
Oh, yes.
Like looking at turf raw soils.
Uh-huh.
So I'm interested in like what is the temperature ranges?
Yeah, so mostly the issues with the top 90 equation was that it's a third degree empirical fit done on wetting and drying curve. They've only gone in between like, let's say 0 and 30. So it just does not have any of the crowded condition range. The way I developed this model with ice crystals in mind, so there's a part of the solver that think about like ice volume expansion and also the adaptive dielectric conductivity of water through a range of temperature, also as it freezes. So it should work for literally anything that freezes. There's no conditions for it to not work on values that are too low. But on the ones I've run in the lab, I've only gone down to like -6, -10, because that's where most of my samples would be like nearly completely frozen. But there should be no issue going to as low as you want.
Okay, and we have one final presenter who's joining us virtually, Dr. Connell Miller from Western University. Connell, are you with us online?
Yes, I'm here. Can you see and hear everything, or?
We can hear you, and I'm just going to switch our screen here. All right, Connell, please go ahead.
Okay, great. Thanks for having me. Sorry I can't be there in person. I'm currently in Alberta helping out our hail field campaign right now, so poor timing on my end, unfortunately. But my name's Dr. Connell Miller. I'm the director of the Northern Mesonet Project at the Canadian Severe Storms Laboratory, and I'm also an adjunct professor in the Department of Civil and Environmental Engineering at Western University. So Canadian Severe Storms Lab, kind of a new concept we launched in October. If you want to know more about it, I am talking about it tomorrow morning in Gallery B, so feel free to come on out. But essentially, we're looking to be the authoritative source for severe convective storms research and data in Canada, and to advance the detection and documentation and understanding of severe convective storms. You may have heard of some of our other sub-organizations under the Canadian Severe Storms Laboratory, such as the Northern Tornadoes Project, the Northern Hail Project, and launched alongside the Canadian Severe Storms Lab, the new Northern Mesonet Project. I'm sure most people know what a mesonet in the room is, but a little bit of a trickier concept to explain to the general public than tornadoes or hail are. So essentially, mesonet is just a portmanteau of the words mesoscale and network. These include things like thunderstorms, downbursts, tornadoes, and they last from several minutes to several hours. Therefore, a network of densely spaced surface weather observations are required to ensure that these mesoscale weather events do not go undetected. And the surface weather observation part of that is really, really important. Yes, radar is great for precipitation analysis, but when it comes to some of these things, once you get further and further away from a radar, you risk losing some of that data when it comes to these severe convective storms. And we really do care about these severe convective storms because they impact Canadians. Just in 2024, we had the Jasper wildfire. This is a path of a suspected fire tornado. We're doing a lot of work to try to confirm that right now. That happened with the Jasper wildfire here. $900 million worth of insured losses. The Toronto flooding, same year, almost $1 billion in insured losses there. And then, of course, the Calgary hailstorm, $3.2 billion worth of insured losses. So quite the year in Canada in terms of these severe convective storms. If you look at the top 10 insured losses from these natural disasters, you'll notice a few things. Number one, 5 out of the 10 of them are from some form of severe convective storm. And 6 out of the 10 of them are from the last 3 or 4 years, right? So we're starting to really notice a trend of, because we're building in areas that are prone to these events, the damages start to rack up more and more over the years. So again, these surface weather stations are very important for trying to analyze some of the data of that. The problem is lots of different agencies own these surface weather stations, and the data from these agencies can vary in ease of accessibility. This makes it really challenging to analyze the data in real time for severe convective storm nowcasting, or to even examine the data after a major severe convective storm has gone through. So that's why we started the Northern Mesonet Project. And currently the Northern Mesonet Project, our main goal is to connect and enhance Canada's weather networks. And we're doing that in 2 main ways. The main focus of this talk is going to be on the Canadian Mesonet portal, but I'll touch briefly on our own network of stations as well. So what is the Canadian Mesonet portal? It's a network of surface weather station networks. And I'm going to hopefully give you a live demo here, and I'm praying that this works across the virtual landscape here. If it doesn't, if you're not seeing a Canadian Mesonet portal here, eventually somebody stop me, please, before I keep talking. So this is our Canadian Mesonet portal. So you can see the 2,824 stations that we're currently reading across Canada. As you zoom in, you'll start to get more meteorological data from these different weather stations here. We have a lot of filtering tools here, so you can see the 30 or so networks that comprise these stations. So if you're in here and you want to say, okay, I only want to see the stations from Alberta Agriculture, you can do that. Or let's say that plus MSC and Nav Canada, we can do that as well. If you only want to see stations that are reporting certain variables, we can do that as well. So if you want to get rid of anything that's not reporting wind, those disappear off the map for you. I'll throw our own weather stations in there as well for fun. If you want to see stations that have only updated in the last 30 minutes to the last hour to the last 6 hours, you can add that as well. There are also lots of different layers that you can put on top of it. So if you want to see the geostationary satellite, you can do that. If you want to take a look at the radar, it looks like it's about to be raining where I am. You can do that as well. We have some other ones as well, including lightning density, the weather alerts. So if you want to pop that open and see what weather alerts or watches that Environment Canada has put out, you can do so there. We also have some other options here. So I'll mention the MERMS mesh here. This is for the maximum estimated size of hail. It gives you a few options here. So the last 30 minutes, but if you look at, let's say, the last 24 hours here, we can go down to Texas here. I believe they had some quite record-breaking hail here, and you can see that pop up on the map. You can also extrude it. So if you want to see the 3D view of the stations or the mesh there, you can do that as well. Some other viewing options that we have as I make my way back to the fun side of the border. We have, right now we're looking at like a standard meteorological view, but if you just wanted to see temperature, you can do that. You can also change like when this changes from dots to the actual view here. So if you wanted a more zoomed out view of Alberta, you can change the cutoff there so that you can see it in a more easy way there. And then finally, we can, if we go, let's take a look maybe at the Calgary airport here. You can graph any of this data here. So we can open this up here. If you mouse over it, you'll get the exact values. If you drag and click, it'll zoom in to that specific time range and give you the average high and low. You can click through the different variables you want to see. So for example, if you wanted to see the wind speed, you could do so there with different averaging periods. So the 1 minute, the 2 minute, the 10-minute average, et cetera, et cetera. You can also add charts so you can see multiple things at the same time here if you're trying to compare and contrast different things. Additionally, you can click the info button to learn more about these different things. Eventually, I'm hoping these will link to some of the catalogs that Kristine mentioned earlier, or some of that Oscar information to give you some more information about metadata about these stations. For now, they're just sort of blank. And finally, once you've got a view that you like and you don't want to have to set up everything again, you can click this export button right here. And it gives you a special link that you can copy and paste into your clipboard there. And it'll bring you back to the exact same spot here with the exact same filters applied. Move back to the presentation here. So some upcoming features that we're going to be adding in the next few months. Historical views. So right now we only have the past week's worth of data visible. We've been archiving it for a little while now, since last October. So we're going to finally be able to have an option to be able to show that and to have the surface map actually change for whenever you want to see it. So you can go back and create historical surface maps for different events that have gone through. We're also going to be creating severe weather summaries. So this will be a daily interactive map that will be automated and pushed to our website that will summarize severe convective weather from the previous day. It'll include things like rotation tracks, the mesh tracks, lightning observations, and surface weather observations from stations that have experienced severe weather on that day. So winds that exceed 90 kilometers an hour and precipitation rates, et cetera, et cetera. We're also working on exporting the data as well as creating some quality control warnings and things like that to go along with that. I'll also briefly mention our own network. We call these storm networks. So because if you don't have a good acronym for something, why are you even bothering? So this is the Severe Thunderstorm Observation and Research Mesonet. The goals of this are to provide the best possible surface-based observations for detection and nowcasting, and specifically to evaluate specialized instrumentation built to handle extreme weather here. So you can see we're testing our hail disdrometers here with a hail cannon. So this is our hail network that we have in the Calgary region. We have 21 stations in Calgary, as well as 8 stations east of the Rocky Mountain foothills. It's composed of 2 instruments here. The all-in-one weather station really isn't anything all that special, but it gets you the stuff that you need. What we're really evaluating here is our hail flow sensor. So this gives you the number of hailstone hits in the area, as well as the distribution of hailstone sizes. And again, half the reason we wanted to build this Canadian Mesonet portal is we've had this network of stations for a while now, and we needed a way to be able to show these hail readings in an appropriate way. So we're finally able to start showing that. Thank you for your time. I'm happy to take any questions that you might have. And my email, nmp@uwo.ca, is at the bottom there.
Great. Thank you very much, Connell. Any questions for Connell in the room? Yes, go ahead. I'll repeat the question, Connell, in case you can't hear it.
Okay. Yeah, I haven't been able to hear any of the questions.
Yeah, there's a microphone right there.
So much of a question more than a comment of appreciation for all the different the word I'm looking for functionalities that you showcase, because I feel like we can definitely tell that it's done by scientists for scientists. That's great. So thank you.
Yeah, thank you. I appreciate that. And we're always open to new features. So, and from different research groups. So if you've got a research project or you say, hey, I think this would be helpful from a research perspective, feel free to email us. We're very open to adding new things as we go here.
Well, what you mentioned in your presentation about adding like past data, like past a week, that sounds great.
Yeah, thank you. Hopefully next month that'll be ready to go.
Any other questions for Connell? I can walk the mic over to people too, if that's easier. Yes, Renee, go ahead.
It's stuck. I'm Virginia. I'm the climatologist at Saskatchewan Research Council. I was wondering where you were pulling all that data from. Is it Datamart?
A lot of it is from Datamart. Some of it is external. So right now we have a few networks that are external, one being our own hail network, as well as the University of PEI's network, as well as Hydro-Quebec. So we have a few, but we're starting to talk with Environment Canada, and I think the strategy going forward is going to be trying to get as much onto Datamart as possible, and then for us to act more of as a front end to see this data.
Perfect. And are you going to let these organizations know that you're pulling the data off Datamart?
Yeah, absolutely. So we've had conversations with the Canadian Weather Council, the Monitoring Council. Sorry, we've presented all of this to them. Most of them seem pretty thrilled to be seeing this data. We're also going to be developing an administrative dashboard that we will give access to these different stations so that they can see what data of theirs is being reported and any quality control flags that Datamart might be flagging for them to be able to see that and interpret that. So we're going to be providing some back-end access to this to these weather monitoring services.
Okay, thanks.
Yep.
Thanks, Virginia. Yes, yeah, Colin and I are definitely connected, making sure we draw the connections between our two programs. Any other questions in the room or online? No? Okay.
What's the price tag for this?
The question in the room, Connell, what's the price tag for this project or initiative?
So far, just my time and a few undergraduate students' time. So far, pretty low. I think for our hail stations, they're about 15,000 to 20,000 each to install, plus a few hundred a year for maintenance and data costs and things like that.
Thank you. Okay, well, if there are no further questions, thanks very much, Connell. Appreciate the time and attending virtually. That was great. And for all of our presenters, really interesting work to hear everything that people are doing across the country related to monitoring and improving data collection for various applications. So that concludes our session for this afternoon. I hope everyone enjoys the rest of the day and the rest of the conference this week.